Students, myself Professor Ankur. I welcome everyone for the gate theory session on analog circuits. Today we are going to discuss an important topic from differential amplifiers, that is differential amplifier gain equation, and we will take a small example on differential amplifier. So let's start with the session 2 on differential amplifiers. So in the previous session, we have actually seen the four types of differential amplifier. And if you are able to recollect carefully, the four different types of amplifier were defined in terms of dual input, dual output, dual input, single input, dual output, and single input, single output. And with respect to the definition of balanced and unbalanced, we had balanced input, balanced output, balanced input, unbalanced output, unbalanced input, balanced output, and unbalanced input, unbalanced output. So this is the way we define the four types of differential amplifier, starting from left going towards right. Now, we need to understand an important point regarding the definitions of gain. So here we can see carefully that there are four differential amplifiers. So the four differential amplifiers here are dual input, dual output, dual input, single output, single input, dual output, and single input, single output. So they can be defined as balanced input, balanced output, balanced input, unbalanced output, unbalanced input, balanced output, and unbalanced input, unbalanced output. So any of the amplifiers will have in all 5 parameters. The first parameter will be defined as differential gain, defined as AD. The second parameter will be defined as common mode gain, defined as AC. Many of them actually also define this as ACM, standing for common mode. The third parameter is CMRR, common mode rejection ratio. That is basically the magnitude or the mod of AD by AC. Then we have input resistance of the differential amplifier and output resistance of the differential amplifier. So these all things can be derived using the AC equivalent circuitry. So we are getting the outcomes. I will discuss all the outcomes one by one. When we talk about balanced input, balanced output, the value of AD is going to be GMRC. AC will be minus of RC by twice of RE. CMRR will be twice of GMRE. RI will be twice of RPi. RO will be RC. When we talk about balanced input, unbalanced output, differential gain AD will be GMRC by 2. AC will be minus of RC by twice of RE. CMRR will be GMRE. Input resistance will be twice of RPi, that can be taken as twice of beta RE. RO will be equal to RC. So if your observation is very sharp, the common mode gain is actually the same. The differential gain under unbalanced output configuration has reduced to half the value that we got from balanced output configuration. So that's the reason even the CMRR has gone to half of its value that we have got in the balanced input, balanced output configuration. Next is unbalanced input, balanced output. The value of differential gain AD is going to be GMRC. The common mode gain AC will be minus of RC by twice of RE. CMRR will be twice of GMRE. Input resistance will be twice of RPi, that can be taken as twice of beta RE. And output resistance RO is going to be equal to RC. The last case is unbalanced input, unbalanced output. The differential gain is again GMRC by 2. Common mode gain is minus RC by 2RE. So CMRR will become GMRE. Input resistance is twice of RPi and output resistance is RC. So if your observation is very sharp in this table, you can actually figure out that whenever we talk about balanced output logic, the differential gain is GMRC, And under unbalanced logic, we get it as GMRC by 2. And on similar lines, when you see the row for AC, all the configurations are having the same common mode gain. But when we talk about CMRR, the CMRR under balanced configuration, balanced output configuration gives you twice of GMRE, and unbalanced gives you GMRE. The input resistance in all four circuitry is approximately equal to twice of beta RE, that is twice of R pi, and output resistance will be equal to RC. So this is how you can compare the all four types of differential amplifier in terms of its differential gain, common mode gain, CMRR, RI, and RO. So here we are having a question, and the question says the following specifications are given for dual input balanced output differential amplifier with RC equal to 2.2 kilo ohm, RE equal to 4.7 kilo ohm. The internal resistances of the source defined as RE1 and RE2 equal to 50 ohm, VCC as 10 volt minus VEE as minus 10, beta DC is equal to 100, VBE equal to 0.715. Determine the operating point ICQ and VCQ for two transistors. So since it is balanced input, balanced output configuration with respect to the center imaginary line, I can easily observe that the left hand side circuitry and the right hand side circuitry will be the same. So if I analyze any one of the sides, it is going to give me the result for the other side. So now when I go for the calculation, I will go for KVL to the input loop. From that, I will get the value of IB and can be modified into IC or IE by just multiplying it by beta. We are assuming here that IE and IC are actually same. So with that logic, I can define ICQ or IE is equal to VEE minus VBE divided by twice of RE plus RIN divided by beta DC. So this is the derived equation. On substitution, you get the value of IEQ or ICQ as 0.988 milliampere. Now when we go for the KVL to the output loop, you will get the value of VCEQ as VCC plus VEE minus ICRC minus IC into 2RE. On substitution, you will get the value of VCQ as 8.5392 volt. So this is how you calculate the value of ICQ and VCQ for a differential amplifier. Now the advantage that we get here is whether we talk about any of the category of differential amplifier, whether it is balanced input or unbalanced input, or balanced output or unbalanced output, in either of the cases, the equations for DC will almost remain the same, because during the DC, the AC point or the output point is not considered, and we can easily solve with respect to the input section with AC source as shorted and only with the DC values. And that's the reason it's very easy to calculate the current and the voltages of the differential amplifier. Thank you.